Welcome back to the deep dive. Today, we're going to step away from the easy fixes, the seal lintels, and get back to the pure, elegant logic of structural masonry. We are sinking our teeth into the king of brickwork, the Masonry Arch.
It really is, isn't it? It's the ultimate sign of mastery in our trade. I mean, if you can lay a plumb, symmetrical, and structurally sound arch, you're a master mason. Simple as that.
For sure.
And it's not just some Roman relic. The history of this thing, as our source notes, it goes all the way back to 1400 BC in Babylonia. Think about that for a second.
1400 BC?
Yeah. Archaeologists found an arch there, built with these well-baked cigar-shaped bricks laid in clay mortar. It's possibly the oldest structural arch known to humanity. It predates the Romans by a mile, predates almost everything we think of as classical architecture, but the physics...
The physics are identical.
Identical.
And so here we are, thousands of years later, and it's still the gold standard. It's the piece of work that separates the apprentices from the journeyman. We know a lot of you moving into curved work, you look at an arch and you just see, intimidating geometry, complicated math.
Right.
That's our mission today. We're going to take the technical notes, the history, the physics, and just demystify the geometry of strength so you can walk onto that job site and approach the layout board with absolute confidence.
And our core philosophy here, our motto, it's simple, but it's absolute. You got to adopt this. The brick arch is the perfect example of form-following function. Its aesthetic appeal is undeniable, sure, but the reason it works is just pure physics. It's all about managing the forces of gravity.
And that magic word is compression. This is the key. Masonry brick, stone, block. It is so much stronger when you squeeze it than when you try to pull it apart.
Oh, absolutely. Night and day.
You try to pull a brick wall over, it fails easily. You stand on it, it'll last forever. A flat lintel, which is our modern shortcut, is always trying to bend in the middle. It's got tension on the bottom edge and compression on the top.
And tension is the absolute enemy of masonry. The arch just flips that whole equation on its head. By giving the load a curved path, the structure makes sure that under load, the stresses are pretty much all compressive.
All squeeze.
All squeeze. It is the most efficient structural element to span an opening for that exact reason. It takes that heavy vertical weight, and instead of letting it bend the element in the middle, it turns it into a powerful lateral push.
So it takes gravity, which is your enemy, and a flat beam, and it makes it the mortar that holds your arch together.
Exactly. An arch never sleeps. It's always working, always pushing. And that push, that intense horizontal force, that's what we need to analyze, calculate, and most importantly, contain.
Okay, let's unpack that. Let's dive straight into section 1. Function the physics of the arch. We need to understand exactly how we turn that vertical weight into the mighty lateral push, and why that push, the thrust, is actually our friend as long as we can contain it.
The compression principle is where it all begins. If you think about a straight beam, a lintel, it has to fight the bending moment from the load above it. That fight introduces what we call flexural stress.
A fancy term for bending.
Just bending stress, yeah. And that means you get tension at the bottom edge. Masonry can only handle a tiny bit of tension before it cracks and fails.
But the curve of the arch changes the whole geometry of that load path. It's not a lever being pulled down anymore.
Precisely. The curvature lets the arch transfer those vertical loads laterally, sideways, along the curved path of the arch itself. It distributes the force all the way down to the supporting structure, to the abutments.
It's moving down and out.
Down and out. And that movement ensures that the internal forces are a combination of some flexural stress, but crucially, axial compression.
So the load isn't just dropping straight down in the middle. It's kind of sliding outward and down, getting squeezed tighter and tighter as it gets to the shoulders of the arch.
That squeezing, that axial compression, that's the genius of it. And by manipulating three things, the arch depth, the thickness, the rise or the height, and the overall shape, the whole goal is to manipulate that load path, what we call the line of thrust, to keep those internal stresses overwhelmingly compressive.
Because brick loves compression.
Brick loves compression. A well-designed arch can support immense loads, way more than any lintel of the same material could ever handle.
And that transfer of force, that sideways slide we keep talking about, that's where we meet our most critical concept, lateral thrust.
Thrust is the horizontal part of the reaction that happens at the abutments. When that vertical load gets channeled down and out, Newton's third law kicks in. For every action, there's an equal and opposite reaction. So the load pushing down and out, it generates both vertical and horizontal reactions at the support. That horizontal force is the thrust, and it develops in all arches. Every single one.
And this horizontal push is what makes the arch so unstable until it's properly held back. It's this constant outward pressure.
Correct. And this is where the map can feel a bit tricky, but the core relationship is really simple, and it's something every mason has to grasp. The shape dictates the push. The more shallow or flat the arch is, the harder it pushes sideways.
We have to camp out on this for a second because this is probably the single most critical detail for a structural mason. Understanding that shape-to-thrust relationship.
It is. The thrust force is significantly greater for flatter arches, like a jack arch, than it is for a high-rise arch, like a semicircular one. And the reason is a high arch, because of its steep curve, directs most of the load almost vertically downwards. The horizontal part is minimized.
It's like a ramp.
Yeah, exactly like a ramp. A steep ramp is easy to stand on without sliding, but a very shallow ramp, requires a massive horizontal force to keep you from slipping.
So if you're spanning a wide opening, but you have a lot of height to play with, say a big bridge or a cathedral doorway, a high arch is better structurally because your abutments don't have to fight as hard against that push.
For sure.
But if you've got limited headroom and you have to use something like a jack arch, you are signing up for a monumental amount of outward thrust.
And that commitment brings us right to the abutment. This is your support structure. It could be a massive column, a continuous wall, or a combination of masonry and steel, whatever. It supports the arch at its starting point, the skewback. The arch is only as strong as its shoulders. If the shoulders give way, the arch falls.
And what's crucial, and what most people don't realize, is that an arch failure almost never starts in the middle, at the keystone.
No, not at all. Failure happens, overwhelmingly, from excessive lateral movement of the abutment caused by that horizontal arch thrust. When the abutment moves outward, even just a little bit, the line of thrust shifts, the bricks lose that necessary compression, and the arch collapses.
So the abutment has to be incredibly rigid.
Incredibly rigid. If it's inadequate, the whole system fails, often catastrophically.
So let's talk about that rigidity in a modern context.
Yeah.
In hybrid construction, sometimes we have to tie a masonry abutment into a steel column or a concrete frame. How do we anchor that rigidity? Our source notes get really specific on this.
This is a critical technical nugget that apprentices, they often miss this. When you're joining masonry that serves as a structural abutment to a non-masonry member, you need to use adjustable ties or single or double rigid wire ties.
Rigid wire ties, why is that so important? Why that specific type?
It's all about axial stiffness.
Axial stiffness.
Yeah, axial stiffness means the tie resists movement along its own length. It doesn't stretch or deform easily under that horizontal pressure. When that arch starts pushing with thousands of pounds of force, that tie needs to lock the abutment down instantly. If the tie stretches or bends, the abutment moves, and even a millimeter of movement can compromise the whole compression line in the arch.
And this brings us to the big no-no, the corrugated ties.
Correct. What you absolutely have to avoid in this specific structural application are those standard corrugated ties, the flimsy ones you see on veneer walls all the time. They have almost no axial stiffness. They're designed to allow a little bit of movement between the veneer and the structure, which is fine for seismic, but it's a disaster for an arch abutment.
So what does that failure look like down the road? If a mason uses a corrugated tie on a structural arch abutment, what happens?
Well, that tie will deform. It'll stretch before it fully engages the structural member. That tiny initial movement lets the arch abutment creep outward, maybe just a 1/16 of an inch, but that's enough. That slight outward movement relieves the compression in the arch, and you'll start to see hairline cracks appear near the crown and the springing line.
And over time?
Over years, with thermal cycling and gravity, those cracks widen, and the arch just loses its structural integrity. You need the rigidity of a solid wire or an adjustable tie, not something designed to flex.
Lock down the abutment, contain the thrust. Got it. Now let's move to the absolute starting point, the piece that determines the success of the whole curve. The skewback. This is where layout moves from theory into, well, a physical structure.
The skewback is the surface where the arch physically joins the abutment. It's the prepared angle, could be horizontal, vertical, or angled, that accepts that very first voussoir. The skewback angle is the angle this surface makes from the horizontal, and this is where that lateral thrust is first channeled into the wall system.
And this is where my world, the layout world, becomes a structural necessity. If an apprentice gets this wrong, everything that follows is compromised.
Absolutely.
This is our layout expert focus tip for the day, and I tell this to all my students. If your skewback is off by a degree, your keystone will be off by a mile. It literally sets the radial alignment, the angle of direction for every single brick that follows.
Can you break that down? The cascading consequences of a bad skewback cut?
Sure. If your skewback angle is too steep or too shallow, that first brick, the springer, it's going to be laid at the wrong radial angle.
Yeah.
Now you've got two choices, and they're both bad. One, you can start fudging your mortar joints, making them thicker or thinner to try and correct the curve. That leads to messy, inconsistent, and weak joints.
Structurally weak.
Right. Or two, you can keep your joints consistent, but that means when you get to the crown, your final keystone is either going to be too tight to even fit in, or it's going to be so loose that you have to shove in a massive mortar joint, which completely compromises the compression at the most critical point.
So that initial angle has to be perfect.
It has to be perfect. It is the baseline for gravity's path. For a semicircular arch, that skewback might be perfectly horizontal. For a segmental arch, that skewback has to be cut at a precise angle to directly oppose the inclined thrust. That cut is the foundation of the curve.
And the quality of that cut affects not just the look, but the structural integrity for the next 100 years.
Okay, that gives us the physics, the compression, the thrust, and the critical role of the abutment and the skewback. Now let's get into section 2. The anatomy. Before we can build it, we need the language of the trade to talk about these curves. Let's get specific.
Good idea. Let's start with the curves themselves, the lines that define the shape. The curve that bounds the lower edge of the arch, the one facing the opening, the one that defines the shape you walk through. That is the intrados.
And the actual surface that's created by that inner curve, the part you look up at when you walk under the arch, that's the soffit. Small distinction, but an important one. The intrados is the line, the soffit is the surface.
Right. And moving to the top, the curve that bounds the upper edge of the arch, the line that meets the surrounding wall, is the extrados. And right at the very top of that extrados, at the midspan on a symmetrical arch, is the crown.
That's high point.
That's the high point.
Yeah.
It carries the maximum load, but because the arch mechanism is working, it's also the area of maximum compression.
We also need our basic measurements. The clear horizontal distance of the opening between the abutments, that's our span, and the vertical lift, the maximum height of the soffit above its baseline, that's the rise. Rise and span.
Those two numbers define the whole structure.
And that baseline you mentioned is known as the spring line. It's the horizontal line that joins the two springing points. That's the point where the skewback meets the intrados. Those springing points are the anchors for your rise and span, and they determine where your centering begins.
Okay, now for the building blocks. Every single masonry unit that makes up the arch, the wedge-shaped piece, that's called a voussoir. That's right. And I'm not going to tell a joke about sending the apprentice for the left-handed voussoirs.
He's still in the tool trailer 45 minutes later.
He's still looking for them. So the very first voussoir, the one right next to the skewback, that's the springer. It starts the curve, and it accepts that initial transfer of load from the abutment. If your springer is laid wrong, the whole arch is unstable from the get-go.
And then the piece everyone recognizes, the final piece that locks the whole machine together and basically turns gravity on, the keystone.
The keystone is the voussoir right at the crown. Its structural function is to provide that final bit of compression that's needed to make the whole structure self-supporting. The moment that keystone is seated, the arch isn't a pile of wedges on a form anymore. It's a self-sustaining structural element.
It's the on switch for the arch's strength.
That's a great way to put it.
And there's a specific structural advantage to using a large keystone, isn't there? It's not just for looks.
Absolutely not. This is a key insight for design. When an arch gets overloaded, or it settles more than it should, the most likely place for the first crack to appear is in the mortar joint, right next to the keystone.
Because that's the point where the opposing forces from the two sides meet, and where tension, our enemy, might try to sneak back in if the compression fails a little bit.
Precisely. So by using a large keystone at the crown, making it deeper along the intrados, you effectively push that vulnerable joint further away from the center of the span. That increases the arch's resistance to cracking right at that weak point. A big key buys you a structural safety margin.
So the size of the keystone is a structural safety measure. Now, what if that keystone is complex, maybe a composite piece of stone or terracotta?
Yeah.
What's the practical detail we need to watch out for?
Right. If your keystone is made of more than one piece, say a decorative piece over a structural wedge, you have to avoid placing the smaller unit at the bottom near the intrados.
Why is that?
Because when the arch settles under its final load, that smaller unit being at the bottom of the compression line is much more likely to just slip out. And that compromises the integrity of the key and can lead to immediate failure. Always make sure the biggest, most structurally sound piece is in the compression zone at the intrados.
That is a detail that separates the pros from the amateurs, for sure. Now, we should also define the area around the arch, because this masonry is critical, especially during curing. We're talking about the wall, above, and around the arch.
That's the spandrel. It's the area contained between a horizontal line drawn through the crown and a vertical line drawn through the highest point of the skewback. Functionally, the masonry in the spandrel contributes to the load on the arch, but more importantly, once it's cured, it provides massive restraint against the lateral thrust. It acts like a giant buttress on top of the arch.
So if the spandrel hasn't cured, the arch is basically fighting the thrust all on its own, just relying on the abutments below the spring line.
Exactly.
But if the spandrel is cured, the whole wall structure above is helping pin that arch in place.
Precisely. And that cured spandrel is why we sometimes have to delay striking the center, which we'll get to later. You need the compressive strength of the arch, plus the restraint from the cured masonry buttressing the top of the curve. It turns the arch from a freestanding curve into an integral part of the whole wall.
Okay, we've got the physics of the push, we've mastered the language of the parts. Now let's move to section 3. A gallery of geometry. Arches are classified by the curve of their intrados. While there are tons of historical styles for apprentices in contemporary construction, we mostly focus on 3 main types: semicircular, segmental, and the deceptively simple jack arch.
Let's start with the one that gives us the best structural efficiency if you have the space. The semicircular arch. Its intrados is exactly a half circle. It's a beautiful, structurally sound shape.
And the geometry is clean. That simplifies the layout a lot. The center of the arch lies exactly on the spring line, which gives masons an easy reference point for laying out the radius.
And because it's a perfect half circle, the voussoirs of a semicircular arch are typically all the same size and shape.
Oh, that makes cutting at the bench a lot easier.
It simplifies unit production dramatically, whether you're cutting them in the field or ordering them. They're often used for very long spans. You see them in old bridges because they are so structurally efficient.
And we come back to the physics. Because the curve meets the abutment horizontally at the spring line, the thrust is directed almost perfectly vertically at the skewback.
And that is the key benefit. The abutment only needs to resist a minimal horizontal push compared to its vertical load. That means you need less mass in the abutment wall to contain the force, as long as you have enough height to get that full half-circle shape.
Okay, so contrast that ideal scenario with the workhorse of most modern buildings, the segmental arch.
The segmental arch. Its intrados is circular, but it's less than a semicircle. Think of it as a small slice of a very large pie. It's a shallower curve designed to maximize your head clearance, and critically, its center point lies below the springing line.
That's the layout difference a mason needs to grab onto immediately. If you're laying out a segmental arch, you have to drop your center point below the opening.
And because it's shallower, we go back to the physics. The segmental arch generates significantly more lateral thrust than a semicircular arch of the same span. The thrust is transferred at an angle, an inclined direction, meaning your abutments have to be designed not just to hold the weight, but to fight a serious amount of outward force.
It's the typical arch you see over ground floor windows and doors, right, where you need the span, but you just can't afford the height for a full semicircle.
Exactly. And that means the segmental arch needs a much more robust abutment design than the semicircular, even for the same span. The angle of that skewback has to be perfectly aligned to resist that inclined thrust. It's always angled upward and inward, lining up with the tangent of the circle at the springing point.
And then we get to the deceptively difficult arch that looks like it's cheating gravity, the jack arch or the flat arch.
The flat arch. This is where we tried out our favorite reality check for the apprentices.
I know this one. A flat arch is the only time in masonry where you work twice as hard to make it look like you didn't do an arch at all.
That's the one. It looks like a lintel, but it's structurally an arch, using only compression. It has zero or very little rise. That minimal rise, which is critical for it to work, is called camber.
Right, the camber.
That camber is usually specified as a very slight lift, maybe 10 to 15 millimeters per meter of opening. And that little lift is crucial because it's an allowance for the settlement that's going to happen when the mortar cures and the arch takes its final load.
Yeah.
Without that camber, the arch would settle and immediately look like it's sagging. A visual failure, even if it's holding.
And even though it looks flat, structurally, we are generating the maximum possible thrust.
The absolute maximum. Flat arch equals maximum thrust. That's why jack arches are only used for light loads and spans typically limited to about 1.5 meters, maybe 5 feet. The geometry requires that the skewbacks form angles of 60 degrees with the horizontal. That 60-degree angle is non-negotiable. It's what ensures the load translates into compression within that shallow depth.
And the depth of the jack arch is usually tied to the surrounding brickwork, isn't it?
Yeah. The depth is typically 3, 4, or 5 courses of the surrounding brickwork. You need that depth to establish the 60-degree angle and to accept that massive thrust.
And there's a variation, the slanted arch, that saves on cutting.
Yeah, the slanted arch is an important one for saving time and money. In a true gauge jack arch, every single voussoir has to be tapered. In a slanted arch, you use rectangular brick for the body of the arch, but you rely on a single, heavily tapered keystone. The joints are still tapered, but the unit cutting is simplified dramatically.
That makes sense. And just to touch on the historical ones, we have the Gothic arch.
The pointed style, yeah. Defines medieval architecture. It's 2 arcs of circles meeting at an apex, which gives you a huge rise-to-span ratio. And because it maximizes rise, it minimizes the lateral thrust. That's how they built those massive cathedrals without the walls falling over. They used flying buttresses to contain the little bit of thrust that was left.
And a couple of others to recognize. The bullseye arch, which is a full circle.
A one-centered arch, yeah. And the Tudor arch, which is that complex, pointed, 4-centered arch with the flat top look.
Finally, the relieving arch.
A purely functional arch. It's built over a lintel, or a smaller arch, for one reason: to divert the loads up and around, relieving the structure underneath. This is how masons could go back and replace a rotten wooden lintel without the whole wall above it coming down. So like structural bypass surgery.
So the arch is always working, always pushing. That's the motto.
Always.
Okay, that covers the structure and the shapes. Now, for the apprentice moving into this work, this is the most critical section. Section 4, the building process. You can draw the perfect arch on paper, but if the construction is faulty, the physics just won't work. We have to start with the temporary component that makes it all possible: centering.
Centering is the temporary shoring, usually a robust wood form, used to support the arch until it's self-supporting. And you have to remember, the arch is unstable until the keystone is seated and the mortar has cured. Until then, it's just a pile of carefully shaped wedges leaning on a wooden form.
And the quality of that centering is everything. It has to be built carefully, it has to be stable, and critically, it has to be marked precisely for the proper positioning of the brick to make sure you get a symmetrical arch.
The centering is the physical template. It has to be built to the exact intrados curve, and it's got to be sturdy enough not to deflect under the weight of the masonry. And the safety criticality here, I mean, you can't overstate it. Premature removal or a failure of the centering will result in an immediate collapse.
Right.
And it'll often take the mason working above it down with it.
Right.
You have to check that the centering is properly braced and shored before you lay that first springer.
Okay, so centering is built, skewbacks are cut perfectly. We move to layout and gauging. This is the bench work, making sure the units fit perfectly without having to shave off pieces at the crown.
And when you're forming the voussoirs, you've got 2 main approaches. And it depends on the design radius, the span, and the look you're after. The first is using tapered or wedge-shaped brick. We call it gauged brickwork. These are custom-cut units that allow for mortar joints of perfectly uniform thickness.
And those uniform joints, same thickness at the bottom as at the top, that's what gives you that crisp, high-quality, historical look.
Aesthetically superior, for sure, and structurally sound because the uniform joint gives you consistent compressive strength. They're also recommended for shorter arch spans, because if you use uncut brick in a tight curve, you'd end up with these massive, wide joints at the top, which is structurally unacceptable.
So the second method, the more common one for longer spans, is using uncut rectangular brick.
In this case, the arch curve is formed entirely by using tapered mortar joints. The joint is thin at the intrados, the inside curve, and it gets wider as you go toward the extrados, the outside curve. But, and this is a big but, we have strict rules for these joints.
What are the limits, and why are they so crucial?
The joints have to be a minimum of 1/8 of an inch, so about 3 millimeters, to get proper bedding, and a maximum of 3/4 of an inch, so 19 millimeters. That 3/4 inch max is critical.
Why?
If a joint gets bigger than that, the mortar itself will compress too much under the load. That leads to excessive settlement, cracking, and you lose your initial thrust resistance. The compression has to be handled by the brick, not by thick, soft mortar.
So when a mason is laying a curved arch with uncut brick, they have to constantly check that that widening joint taper stays below 3/4 of an inch at the top.
Constantly. And that constraint is why the radius matters so much. If your radius is too small, The difference in length between the inside and outside curves is too great, and your joint width will quickly exceed 3/4 of an inch.
So there's a minimum radius for using rectangular brick.
There is, yeah. Our source material references a Table 1, which provides the minimum arch radius for different brick sizes to keep that joint in tolerance. The concept is proportionality. If you need a tight curve, you either need to use a very thin brick or you need to gauge the brick.
And it's important to remember, for something like a semicircular arch, all the voussoirs are the same size. But for a complex curve, like a jack or an elliptical arch, you might need many different shapes from the abutment up to the keystone.
Right, and if you're aiming for uniform joints on those complex shapes, you should absolutely special order those bricks from the manufacturer. They're called arch brick. Trying to cut all those different tapers in the field with a saw will almost never get you the precision you need.
Okay, so everything is laid, the final course is in, the mortar is still wet, the keystone is tapped home. Now we're in the curing and setting phase. This is all about safety and long-term stability.
And the first, subtle but crucial step is easing the center. This happens right after the keystone is placed. The mason performs a very slight, controlled downward displacement of the centering, often just by loosening the wedges, holding the form up.
And you do this while the mortar is still fresh and soft.
Exactly. This controlled easing causes the voussoirs to press firmly against each other, fully engaging the arch mechanism and pre-compressing those mortar joints while they're still plastic. It helps avoid the tiny separation cracks that can develop as the mortar cures and shrinks.
So you're asking the arch to gently take its own weight while the mortar is still soft enough to compress, ensuring maximum brick-to-brick contact. It's the final lockdown.
Precisely. You're engaging the arch mechanism before you take the training wheels off. But when do those training wheels, the centering, actually come off? This is called striking the center.
And the absolute minimum rule of thumb is clear. The centering should stay in place for at least 7 days.
At least. That's the minimum curing time for the mortar to get enough strength to handle the arch's own dead load. But you always have to consider longer curing periods for cold weather or for specific structural reasons.
What are the structural reasons? This goes back to the spandrel masonry, right?
It does. If the arch is truly structural, supporting a lot of weight from above, you might need to wait until the surrounding brickwork, the spandrel, has also cured before you remove the centering. That spandrel acts as a huge buttress against the thrust. If you strike the center before it's cured, the arch has to take the full thrust on its own and you increase the risk of the abutments creeping.
You need the whole system to be rigid.
The whole system. Wait until the wall is ready to accept the push.
Let's transition now to workmanship and durability. We talk a lot about physics and geometry, but if the execution isn't right, the math fails.
And the core rule here is non-negotiable. Fill the joints. All mortar joints in the structural arch must be completely filled, no voids. This is essential for transferring that compressive load smoothly from one brick to the next.
And there's a practical challenge there. If you're laying units in a soldier orientation, standing them up vertically, it can be really tough to get full joints, right?
It's a huge field challenge. The mortar just doesn't want to drop to the bottom properly. In those cases, using 2 or more rings of arch brick laid in the roll-lock orientation lead on their face is often better.
Ah, so the narrow edge faces out.
Right. And the roll-lock orientation creates a much easier path to make sure every single joint is fully packed. You sacrifice a little bit of aesthetic height for absolute structural integrity.
Moving to durability, modern walls are thinner, so water is a huge concern. Flashing is mandatory.
Flashing and weep holes to manage water penetration. Jack arches are the easiest to flash because they're flat. You can use tray flashing that extends about 4 inches past the opening on either side, with end dams to direct water out.
But for the curved arches, segmental and semicircular, it gets a lot harder.
Oh yeah, an order of magnitude harder. For shorter spans, you might find prefab segmented flashing, or you can place tray flashing in the first horizontal joint above the keystone. For longer or tighter spans, you have to use overlapping sections bent along the curve. The detailing can add a lot of complexity.
And here's the critical technical nugget we hinted at earlier. There is a structural consequence to installing flashing.
This is so important. Flashing, by its very nature, is a bond break. If you install flashing above a structural arch, 2 serious things happen at the same time.
First, the load on the arch goes up.
It does. By putting in a smooth, non-adhering surface, you break the bond between the masonry above and the arch itself. That means the load gets concentrated onto the arch's crown instead of being distributed.
And second, the arch's own resistance goes down.
Concurrently, yeah. The structural resistance of the arch is reduced because you've broken the composite action with the spandrel masonry. The arch relies on that spandrel being bonded to it to resist rotation. So it's a double whammy.
Yeah.
You increase the load and you decrease the strength. This has to be considered in the design.
Okay, we've saved one of the most crucial detailing points for last because it links right back to that massive lateral thrust, expansion joint placement. This is a safety issue.
This is non-negotiable information. In long masonry walls, you need expansion joints for thermal movement. But you have to be so careful where you put them around an arch.
Because the arch abutment isn't just a regular piece of wall, it's a highly compressed pier of masonry.
It's doing a monumental amount of work resisting that arch thrust. So vertical expansion joints should not be placed directly above a structural arch. That spandrel area needs to be a monolithic mass to buttress the curve. You put a joint there, you create a weakness.
And what about near the springing line, where the arch starts?
Even worse, do not place vertical expansion joints close to the springing line. The arch abutment needs its full width to resist the horizontal thrust. Placing a joint there is like cutting a slice out of a critical column. It drastically reduces the effective width of the abutment and compromises its ability to resist that push.
So you're basically giving the thrust an easy way out.
You are actively sabotaging the structural geometry. You are creating a path of least resistance for that push to exploit. The expansion joint has to be placed far enough away from the arch and its abutments to preserve the continuous mass needed for thrust resistance.
So we've learned the arch is an elegant machine, but its stability is dictated by the perfect layout at the skewback, the perfect fit of the voussoirs, and the immovable resistance of the abutments.
Success relies on understanding the physics, the geometry of the push. But perfection relies entirely on the prep and the layout. The key is always in the setup. The centering, the skewback angle, the abutment mass, it all has to be perfect to make gravity work for you, not against you.
Which brings us to our final thought. Historically, arches created these huge, uninterrupted wall sections. You think of those massive bridge piers or cathedral walls. They were solid buttresses, and they had to be, to resist that relentless horizontal push.
And when we consider modern masonry, which uses smaller wall sections and requires expansion joints, we have to remember that arch abutments are uniquely sensitive to movement.
So if you put an expansion joint in the wrong spot, you're not just accommodating thermal movement. You're actively challenging the arch's ability to resist its own push. You're creating a failure point in the most critical structural component.
So the question to leave you with is this. How much does a tiny misplaced seamel, a 3/8-inch slice of compressible sealant, undermine the structural strength of a monumental structure? What are you going to look for first on your next job site to ensure the layout expert did their job right at the springing line and that the design didn't just cut the abutments in half?
Think about that rigidity and the constant internal pressure of the arch mechanism. Knowledge applied is knowledge mastered. We hope this deep dive helps you approach your next curved project with the confidence that comes from understanding exactly how gravity holds it all together.